Welcome to the basic mathematics. The probability. A review. Good morning. Every morning we think, is it likely to rain later in the day? Or what are the chances of getting 6 if I roll a dice? Or toss a coin? Such statement relates to level of uncertainty, or indeed a level of certainty. It is this element of likelihood in which we are interested in. In particularly, we need to find the measure of this likelihood. That is associated probability of particular event. Probability of any event is likely of getting a favourable outcome. To find the measure of success in any event, we need to do a long-term experiment, and to find the frequency of happening favour event. The experiment is repeated in such a way that series of independent and identical trials are produced so that the particular event A is observed to either to occur or not to occur. Let n be the total numbers of trials carried out, and n(a) the number of times of that event A was observed. The ratio of n(a) divided by n is the relative frequency of the event A. This value provides some indication of likelihood of event A occurring. Let us toss a coin and note down the outcome of each trial and plot them on a graph. This the graph of relative frequency versus number of trials. As number of trials increasing, we are heading towards a fixed figure. Note, after 100 events, it is almost 1/2 or 0.5. The experimental probability. Here we define the probability P of successful event A as P of successful event, or P in brackets A equals number of successful outcomes, N in brackets A, divided by total number of all possible outcomes N. So, P A equals N A divided by N. Note, as P A is the ratio of the N A and the N A cannot exceed the N. Hence, The probability is always in fraction of 1, from 0 to 1. If we toss a faulty coin, which has minted, with head on both sides, what is a chance of getting head in such a coin? 100% or certainly we get the head. In such case, the probability is P certainty equals 1. And getting a tail from this faulty coin is impossible. Hence, the probability is P impossible equals 0. If A stand for a particular event, the probability of a happening from certainty to impossible, and is written as P A, and 0 less than and equals to P A less than and equals to 1, the probability that an event A does not happen, not A, is written as P a prime or a bar, and P a prime equals 1 minus P A. An experiment means is an act of throwing dice, or an act of tossing a coin, or an act of drawing a card from a pack of 52 playing cards. Outcome or event is what you expect to get in the experiment. Possible outcomes are all events, or a set of all outcomes. For example, from tossing of a coin, there are 2 outcomes, head and tail. From a throw of an ordinary fair die, there are 6 possible outcomes, 1, 2, 3, 4, 5, and 6. For large number of trials, we find the ratio N(A) divided by N tends to a number called the probability of the event P A, or P A equals N(A) divided by N. We denote probability by P A, or capital P in brackets, event A. Please note, number of successful events N(A) cannot exceed the total number of trials. Therefore, we can say 0 less than or equal to N(A) less than or equal to N. Dividing it by N, we get 0 less than or equal to N(A) divided by N less than or equal to 1. Therefore the probability 0 less than or equal to P A less than or equal to 1 must lie between 0 and 1. A formal definition of experimental probability is if a random experiment is repeated n times in such a way that each of the trial is identical and independent, where N(A) is the number of times event A has occurred. After n trials, then, as number of trials n tends to infinity, the N(A) divided by n tends to probability P A. As number of trials n tends to infinity, the N(A) divided by n tends to probability P A. We will carry out an experiment and provide a graphic of such outcomes, which shows that as n increases, the ratio N(A) divided by n tends towards some value of P, where in fact P equals P A. Such a graph is called Relative frequency graph. Now watch. Such a graph of a trial. Of a die. In such a graph of a trial, of a die, you can see as number of trials are increasing we are getting the correct probability of the events. Note, after 120 trials the probability is almost 1/6, or 0.166. Theoretical probability. Use of symmetry. Theoretical probability is calculated by the possible outcomes by studying the symmetry. The probabilities of winning chance, of 1/2 in a coin, and of 1/6 in a die were found by studying the symmetry of the problem. Two faces of a fair coin are just like each other. So, the probability of head P, H, and that of tail P, T, are equal, as sum of all probabilities equals 1, or P, H, plus P, T, equals 1. Therefore P, H, equals P, T, equals 1/2. The probability of getting an event 1/6 in a die was found by studying the symmetry of the die. A fair die is a cube of equal dimensions and uniform mass. For its symmetry, the numbers on its faces are equally likely to be uppermost. The P1, P2, P3, P4, P5, and P6 are probabilities of events of getting 1, 2, 3, 4, 5, and 6 on uppermost. The probability PA of all faces to be uppermost is same, or P1 equals P2 equals P3 equals P4 equals P5 equals P6. Therefore P1 plus P2 plus P3 plus P4 plus P5 plus P6 equals 1. 6 times PA equals 1, or PA equals 1/6. Theoretical probability versus experimental probability. The probability of landing head when a fair coin is tossed is 1/2. This is called theoretical or expected probability. These theoretical probabilities are dependent on the symmetry of the problem and can be verified by experiment with large number of trials. For example, the probability of getting 5 on uppermost from a throw of a fair die is 1/6. Equiprobable events. We saw equiprobable events like in tossing of a coin, throwing in a fair dice, or drawing of a card from a deck of 52 playing cards. Sometime we have more than one favourable events. In such cases, we define the probability of favorable outcomes as P successful events equals number of successful outcomes divided by number of possible outcomes. Examples to understand probability. In a playing card, the probability of drawing one particular card, say King of Hearts, from a pack of 52 cards, P K Black Heart equals N K Black Heart N equals 1 divided by 52, and the probability of drawing an ace, any of the 4 aces of hearts, diamonds, spades or clubs, P aces of hearts, diamonds, spades or clubs equals N for aces divided by N equals 4 divided by 52 equals 1 divided by 13. In case a pack carries 2 additional cards printed as Joker, the probability of drawing an ace will be 4 divided by 54. The letters of word mathematics are each written on a separate piece of paper and put in a bag. Number 1. What is the probability of getting a piece of paper with M, the sample space S's? S equals EMATHEMATICS has 11 outcomes. Therefore N S equals 11. The letter M occurs 2 times. So N M equals 2. Therefore the probability of getting letter M equals N M divided by N S equals 2 divided by 11. The letters of word mathematics are each written in on a separate piece of paper and put in a bag. Number 2. What is the probability of getting a piece of paper with a vowel? The letters which are vowels equals A, E, A, I. Therefore N vowel equals 4. And the probability of getting a vowel equals number of outcomes as vowel N, A, E, A, I divided by N, S equals 4 divided by 11. Set language is often used in probability work, so some of the basic ideas of probability are given again in simple language of set. Before we move further, let's recollect set theory and its notations. As set language is often used in probability work, so some of the basic ideas of the set theory are given here. In mathematics, any well-defined class is called a set. A set of cities of England, London, Liverpool, York, Birmingham, Newcastle, Manchester. A set of 50 states of USA, or set of oceans, etc. Anything belong to a set is an element or a member. Note: a set of even numbers is a subset of a set. of natural numbers. Let's make a set of numbers from numbers 1 to 15, and we list the number of subsets: A, the prime numbers; B, odd numbers; C, multiples of 3 and 4. Call these sets as A, B, C, D. Set A are 2, 3, 5, 7, 11, 13, 17, 19. Set B are 1, 3, 5, 7, 9, 11, 13, 15. Set C are 3, 6, 9, 12, 15. Set D are 4, 8, 12. Intersection of set. The set A and set B both contains element 3, 5, 7, 11, 13. These are common to both. The set of common element is called intersection of A and B, written as a mathematical intersection symbol B, so that a mathematical intersection symbol B equals 3, 5, 7, 11, 13. Union of set. The set of element of set A and set B combined is called union of A and B, written as a union set symbol B. A union B equals 1, 2, 3, 5, 7, 9, 11, 13, 15. Union and intersection of sets. The set of element of set C and set D combined are called union of C and D. C union set symbol D equals 3, 4, 6, 8, 9, 12, 15. An intersection of set C and D of common elements. C mathematical intersection symbol D equals 12. Empty set. The set D and set B do not have any element in common, so the intersection of set D and set B mathematical intersection symbol D is a set without any element. It is called empty set, written as phi, or B mathematical intersection symbol D equals phi. Equal set. The sets are equal if they have same elements, irrespective of their order. Venn diagrams. To show the relationships of sets by a diagram was suggested by John Venn, English mathematician, using ovals to represent a set. The sets are overlapped if they have common element. Here S represent all space, an AA set. Here S represents numbers, all space, from 1 to 15, and set A equals 2, 3, 5, 7, 11, 13. And set of not A. A prime equals 1, 4, 6, 8, 9, 10, 12, 14, 15. Venn diagrams of a mathematical intersection symbol B. Let's take same sets of numbers from 1 to 15. Set A of prime numbers 2, 3, 5, 7, 11, 13. Set B of odd numbers 1, 3, 5, 7, 9, 11, 13, 15. set C of multiple of 3 equals 3, 6, 9, 12, 15, and set D of multiple of 4 equals 4, 8, 12. Here we show in Venn diagram the common area. A mathematical intersection symbol B equals 3, 5, 7, 11, 13. Venn diagrams of a union set symbol B. Here is Venn diagram of the area of both A and B as a union set symbol B equals 1, 2, 3, 5, 7, 9, 11, 13, 15. Empty set B mathematical intersection symbol D. Here is the Venn diagram of B mathematical intersection symbol D. As there is no common area or element, the set is an empty set. B mathematical intersection symbol D equals phi equals empty set. Here is a Venn diagram, all for sets A, B, C and D. Background set S is also known as universal set, noted sometimes as Xi. All these Venn diagrams are very useful in understanding the probability and help us visualize space for event to happen. The probability. The set language is often used in the probability work. So some of the basic ideas of probability are given again in simple language. Of set, the outcome of an experiment or an action is a single result of an experiment or action. For example, outcome of tossing a coin is getting a head. Set of all possible outcome in an experiment or action is called outcome set. And sample space equals EHT. This set is usually called set S. For example, outcome set sample space for rolling of a dice is set S equals 1, 2, 3, 4, 5, 6. The number of members in any set X is written as Nx. For example, when rolling a die, the outcome set S contains 6 outcome, so Ns equals 6. An event of an experiment or action is any subset of outcome of set S. For example, when a die in one event is getting an odd numbers 1, 3, and 5 is same and equal to other 3 outcome of the event of even number 2, 4, 6 and Na equals 3. In both the cases, please note dice is plural of die. But in modern time dice is used as singular and plural both. When the outcomes are equal, and equally likely, the probability of that event A will occur, given by number of wanted outcome in the event setter, divided by number of all possible outcome of set S. A short way of writing the probability of event A is capital P A. So P A equals N A divided by N S. Probability P of event is getting an odd number 1, 3, and 5, or probability P of odd number equals N 1, 3, 5 divided by N S. P A equals 3 divided by 6 equals 1/2. Strategies in solving probability. In solving probability problems, it is often useful to use some form of diagrams to help us visualize the situation, such as the diagrams are often used as Venn diagram, tree diagram, lattice diagram, Carnot map, or probability table, or any other possible diagrams, such as flow chart, etc. Complementary events. In a sample space, an event A can either take place or not take place. A with macron, not A. Sometimes this A with macron or a bar is also written as a prime. Pairs of events like A and A with macron are called complementary events. For example, when you toss a coin, the event A equals getting ahead has the complementary event A with macron equals getting tail. The sum of complementary events P A and P A with macron gives the total sample space, or all possible outcome P A and P A with macron equals 1, or P A plus P A with macron equals 1. Take another example. When you pick a card at random from a pack of playing cards, the event A, getting a picture card, Jack, Queen, and King, has the complementary event A with macron, not A, equals not getting a picture card, or getting a card with Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. The sum of complementary events P A and P A with macron gives the total sample space, that is, all possible outcome P A and P A with macron equals 1, or P A plus P A with macron equals 1. Venn diagram for complementary event. Total outcome S is shown by a rectangle S. Favourable event A are in an oval, and complementary event A with macron is rest of the area. Combined events. Two or more simple events can occur together, or one after the other. They give a combined or compound event. For example, the result of tossing a coin and picking a card is a combined event or a compound event. So, head on a coin and ace from the deck of cards are a combined events. Similarly, playing a game with two dice is another example. The outcomes of combined sample space are formed by combining two outcomes of separate sample spaces. To explain, we take an example. David tosses a coin, and Bob throws a die. What is the probability that outcome will be a head on the coin and 5 on the dice? The total combined sample space, in this case of coin, HT times that of die, 1, 2, 3, 4, 5, 6, has 12 outcome. It can be shown in a Carnot map or probability table. Carnot map or probability table of two events of a coin and of a die. From this Carnot map or probability table, the combined sample space has 12 outcomes. S equals H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. So N, S, equals 12. Favourable event A, head on the coin and 5 on the dice, is H5. Only one event. Therefore N, H5, equals 1. The probability P, H5, equals N, H5, divided by N, S, or equals 1 divided by 12. David tosses a coin, and Bob throws a die. What is the probability that outcome will be a tail on the coin, an even number on the die? Note them on the table. Favourable event A, tail on the coin and 2, 4, 6 on the die are T2, T4, T6. So N, A, equals 3 and N, S, equals 12. Probability of getting a tail an even number. P, A, equals N, A, divided by N, S, equals 3 divided by 12 equals 1/4. Combined events and Venn diagram. The rectangle in Venn diagram includes space of both A and B. P, combined, is shown by red oval. Mutually exclusive event. The events are said to be mutually exclusive if they cannot happen at the same time. For example, you toss a coin. You can get either head or tail, not both, at the same time. So, the events getting head and event getting tail are mutually exclusive events and do not overlap or intersect. Mutually exclusive event and Venn diagram. Complementary event of event A head is event A with macron tail. A head and A with macron tail are two mutually exclusive events. An addition law. An addition law applies to mutually exclusive event if sometime called or law, because it gives you the probability that one event or another event happens. If A and B are mutually exclusive event, then P, A or B equals P, A plus P, B. This addition law applies to more than two mutually exclusive. If A, B, C are mutually exclusive event, then P, A or B or C equals P, A plus P, B plus P, C. Mary picks a card at random from a well-shuffled pack of 52 playing cards. What is the probability of card being a king of spade K black spade or an ace A, not both at the same time? We know P, K black spade equals 1 divided by 52 and P, A equals 4 divided by 52. The addition law gives P, K black spade or A equals P, K black spade plus P, A equals 1 divided by 52 plus 4 divided by 52 is equal to 5 divided by 52. Addition law and Venn diagram. If A and B are mutually exclusive event, then P, A or B equals P, A plus P, B. Further, picking a card at random from well-shuffled pack of card. What is the probability of card being a king or black, 10? The probability of drawing a king of clubs, diamonds, hearts and spades is n, 4, divided by n, 52, equals 4 divided by 52. And the probability of drawing a black tens, 10 of club and spade, is n, 2, divided by n, 52, equals 2 divided by 52. There are 4 kings and 2 black 10 of club and spade. So we want to find out the probability of either king or black 10. There are 6 cards that we would count as successful. Probability of king and black 10. P, K, B 10 equals 6 divided by 52. Probability of king P, K equals 4 divided by 52. Probability of black 10 P, B 10 equals 2 divided by 52. Therefore P, K, B 10 equals P, K plus P, B 10 equals 4 divided by 52 plus 2 divided by 52 equals 6 divided by 52. Note we add the probabilities. If there are several mutually exclusive possibility, separate and independent possibility, that we count as successful. Sometimes two events are not completely separated or mutually exclusive. Consider, for example, the probability of drawing either a red card or a king. There are 26 red cards and 4 kings. K black spade, K black club, K black heart, K black diamond. But they are 2 kings are also in red card of heart and diamonds. So there are of total equals 26 plus 4 minus 2 equals 28, and not 30 possibility successful cards. 2 events are not mutually exclusive. We cannot add them. Separate possibilities. Probability and Venn diagram. The union of events. A and B, A union set symbol B. A union set symbol B is the union of the sets A and B, i.e., the set of elements that belong to A or B or both A and B. P, A union set symbol B, is the probability that either event A or event B or both occur. From this we have the addition rule for probability. P, A union set symbol B, equals P, A, plus P, B, minus P, A mathematical intersection symbol B. Possibility of space. For 2 events in any 2-dimensional array that shows all possible outcome is called possibility, CON or map. Space when 2 coins are tossed. The possible outcomes are HH, HT, TH, TT. Each outcome is equally likely. P, HH equals 1 divided by 4. And P, TT is 1 divided by 4. By listing the possibility of equally likely outcome, the required probability can be found. Possibility of space. For 2 events of 2 dice. However, if 2 dice are rolled, there are many possible outcomes. We must set out a list in an organized way so that there is no risk of missing any. We can list outcome in a table using crosses. table shows there are 36 possible outcomes. N or n, 36. To find the probability of getting two events, which add up to total score of 5. Color or tick to indicate where the total score of 5 is possible. There are 4 possibilities n, 4. 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1. So P, A, equals n, 4, divided by n, 36, equals 4 divided by 36, or 1 divided by 9. Table shows there 36 possible outcomes. Similarly, we can find the possibility of getting a score of 8. Color or tick to indicate where the total score of 8 is possible. There are 5 possibilities. 2 plus 6, 3 plus 5, 4 plus 4, 5 plus 3, and 6 plus 2. So P, A, equals n, 5, divided by n, 36, equals 5 divided by 36. Dependent events. In the previous exercise, the rolling dice of second time is not influenced by the result of first outcome. Sometime, however, when picking a ball from a bag without replacement, second outcome depends on what happened in the first event. If there are 5 balls, 3 green and 2 red in a bag, and first we pick 1. Now we pick second ball. But bag has now only 4 balls, and the possibility space is different than from the first event. Examples to understand probability. Example 1. In a well-shuffled pack of 52 playing cards, find the probability that a card is drawn at random is heart. There are 52 possible outcomes, n equals n, 52. And since there are 13 hearts, we have 13 favorable outcomes, n, 13. The probability of drawing heart is P, heart, equals n, 13, divided by n, 52, equals 13 divided by 52, or 1/4. Example 2. From a pack of playing cards, the king of heart K is removed. The remaining cards are well shuffled. What is the probability that a card drawn at random is heart? There are now 51 equiprobable outcomes, 12 of which are favorable. Thus, the probability of a card drawn now is a heart is P, heart, equals 12 divided by 51, that is 4 divided by 17. Example 3. From a pack of playing card, 2 cards are taken out, which are not heart. They are not replaced. The remaining cards are then well shuffled. What is the probability that the next card drawn is a heart? There are 50 possible outcomes. Of these, 13 are favourable, since there are 13 hearts in the pack. The probability that a card drawn at random is a heart. Therefore P, heart, equals 13 divided by 50. Example 4. A man has 4 blue socks in his drawer, 8 brown socks and 6 green socks. Find the probability that the first sock he select, followed by next of same color, on one dark morning is 1. Blue, 2. Brown, 3. Green. Since there are 18 socks in a drawer, of these 4 are blue. The probability that a socks are selected at random is blue is P, blue sock, equals 4 divided by 18. Since there are 18 socks in a drawer, of these 8 are brown. The probability that a socks are selected at random is brown is P, brown sock, equals 8 divided by 18. Similar probability that the socks is green is 6 divided by 18. If first sock selected is blue, then there are 3 blue socks remaining in the drawer out of 17 socks. So to make a pair of blue socks, the probability of next getting blue is P, second blue, equals 3 divided by 17. The probability of getting 2 blue socks, P, 2 blue, equals 4 divided by 18 times 3 divided by 17 is equal to 12 divided by 306 equals 2 divided by 51. If sock selected is brown and then there are 7 brown socks remaining in the drawer out of 17 socks. So to make a pair of brown socks, the probability of next getting brown sock is P, second brown sock, equals 7 divided by 17. The probability of getting 2 brown socks, P, 2 brown, equals 8 divided by 18 times 7 divided by 17 is equal to 56 divided by 306 equals 28 divided by 153. Similarly, the probability of getting 2 green socks, P, 2 green, equals 6 divided by 18 times 5 divided by 17 equals 30 divided by 306. Example 5. A number is selected at random from these numbers between 50 and 60 inclusive. Find the probability that it is number 1 prime number, number 2 a number multiple of 8. There are 11 numbers from 50 to 60. Of these, only 53 and 59 are prime numbers. The probability T, hat number chosen at random is prime number, is P, prime number, equals 2 divided by 11. only one number in this range is multiple of 8. That is 56. So probability of that number chosen at random is multiple of 8 is P 56 equals 1 divided by 11. Example 6. 3 athletes A, B and C are to run a race. B and C have equal chance of winning, but A is twice as likely to win as either. Find the probability of each athletics winning. We wish to find out 3 members to assign as probability that each athlete will win the race. Since one runner is certain to win, the total probabilities equals 1. B and C are equal to win and let the probability be X. Since A is twice as likely to win as either, his probability equals 2x. So x plus 2x is equal to 1, or x is equal to 1/4. The probability that a win is 1/2 that of B and C is 1/4. Example 7. A card is randomly selected from an ordinary pack of 52 playing cards. Find the probability that it is either a black card or a king. Let B be the event. A black card is selected, and K the event. A king is selected. The event B has its element all the 26 black cards. This means that B equals 26 black card. And K equals king of spade, of club, of diamond, of heart, so that B mathematical intersection symbol K equals king of spade, of club. Using the addition rule, P, B union set symbol K equals P, B, plus P, K, P, B mathematical intersection symbol K. We have P, B union set symbol K equals 26 divided by 52 plus 4 divided by 52 minus 2 divided by 52 equals 28 divided by 52 equals 7 divided by 13. Note importance of subtracting 2 divided by 52, as this represent the fact that we have included the event 2 black kings twice when finding B and K. Example 8. A bag has 20 tokens, numbered from 1 to 20. A tokens is drawn at random. What is the probability that the token drawn has a number that is divisible by 3 or by 5? We know here total outcomes equals 20. Let T denote the event. The number is divisible by 3. And F, the event, the number is divisible by 5. Now, T equals 3, 6, 9, 12, 15, 18, and F equals 5, 10, 15, 20. And note that T mathematical intersection symbol F equals 15. Therefore, P, T equals 6 divided by 20 and P, F equals 4 divided by 20 and P, T mathematical intersection symbol F equals 1 divided by 20. Using the addition rule, therefore P, T union set symbol F equals 6 divided by 20 plus 4 divided by 20 minus 1 divided by 20 is equal to 9 divided by 20. Equiprobable events. We saw equiprobable events, like in tossing of coin, throwing in a fair dice, or drawing his card from a deck of 52 playing cards. Sometime we have more than one favourable event. In such cases, we define the probability of favourable outcomes as P successful events equals number of successful outcomes total divided by number of possible outcomes. Equiprobable events and its importance. Importance of equiprobable events help us to combine successive events. For example, to find the probability of showing 2 heads in tossing 3 coins, or a coin 3 times successively. Total of all possible outcomes is 2 times 2 times 2 is equal to 8. H H H H H T H T H H T T T H H T H T T T H T T T. The favourable outcomes of 2 2H are 3. So the probability of showing 2 heads P 2H equals 3 divided by 8. Probability using a tree diagram. Three coins are tossed together. Find the probability of number 1 obtaining 3 tails, number 2 obtaining at least 1 head. Note: obtaining at least 1 head is complementary to no head. It means only tails in all 3 toss. That is TTT. We draw now probability trees for 3 coins toss. And notice total sample space are made of 8 events. On first toss, we have either head or tail, followed by again on a second toss, we have either head or tail, and on third toss, we have either head or tail. So total of all events, 2 times 2 times 2 is equal to 8. H H H H H T H T H H T T T H H T H T T T H T T T. Let's A be the event obtaining 3 tails. There is only one event with all tails, so A equals TTT. P A equals 1I8. At least 1 head is in 7 events, leaving only 1 where all are tails. So getting 1 head mean not having all tails, not A. P H equals P A with macron equals 1 P A equals 1 minus 1 8 equals 7I8. Simplified tree diagrams with events of 2 dice. When 2 dice are rolled, what is the probability of getting 3 on one die? An even number on the other die. The probability of getting 3 P3 equals 1 or 6. and P even numbers with 2, 4, 6 equals 3, 6. And left two events 1, 5P, 5, 1 equals 2, 6. So all probabilities adds up to 1. We solve it by making a simple tree. Simplified tree diagram means we make it a compact tree by showing only with relevant branches. We divide it in 3 branches of P even, P3, and other P1, 5 in both the dice. Events of our interest are shown by green branches. Favorable events are P even, 3. 3, 6 times 1, 6 equals 1 or 12. And P3 even number equals 1, 6 times 3, 6 equals 1 or 12. So adding both the probabilities equals 1 or 12 plus 1 or 12 equals 1 or 6. Conditional probability. Informal definition of conditional probability. Conditional probability works in the same way as simple probability. The only difference is that we are provided with some prior information or knowledge, or some extra condition about the outcome. So rather than considering the whole sample space S, given some extra information about the outcome of the experiment, we only need to concentrate on a part of the whole sample space S asterisk. This means that the sample space is reduced from S to S star. Before formalizing this section, we use an example to highlight the basic idea. Example: in throwing a die, find the probability of getting a 2. In second case, now that of conditional probability. After throwing a die, it is noted that an even number appeared. So what is the probability of 2? Part 1 is S equals 1, 2, 3, 4, 5, 6, so P 2 foot equals 1/6. Second case. This time, because we know that an even number has occurred, we have a new sample space, namely S asterisk equals 2, 4, 6. The new sample size is N, S asterisk equals 3. Therefore P2, given that an even number showed up, equals 1/3. Formal definition of conditional probability. If A and B are 2 events, then the conditional probability of event A given event B is found using P A B equals P A mathematical intersection symbol B divided by P B. P B not equal to 0. Note if A and B are mutually exclusive, then P A B equals 0. From the above rule, we also have the general multiplication rule. P A mathematical intersection symbol B equals P A B times P B. It should also be noted that usually P A B probability of event A given event B not equal to probability of event B given event A P B A. Example: 2 dice, numbered 1 to 6, are rolled. Find the probability of obtaining a sum of 5. Given that the sum is 7 or less, we first draw a lattice diagram. From the diagram, we see that the new sample space is made up of 21 outcomes. See red boxes on the lattice diagram, and the event we want are circled on the lattice diagram. Consists of 4 outcomes. By calculation you can note P, x equals 5, mathematical intersection symbol, x less than or equal to 7, P, x equals 5, equals 4/36 and P, x less than or equal to 7, equals 21/36. Therefore, the probability of 5 after getting sum of dice numbers are less than or equal to 7 P, x equals 5, x less than or equal to 7, equals 4/21. Conditional probability. Example 10. A box contains 2 red cubes and 4 black cubes. If 2 cubes are chosen at random, find the probability that both cubes are red. Given that number 1, the first cube is not replaced before second cube is selected. Number 2, the first cube is replaced before second cube is selected. Let the event A, the first cube is red, and event B, the second cube is red, and this means that the event A mathematical intersection symbol B must be both cube are red. P, A, equals 2, 6 equals 1/3, as there are 2 red cubes out of 6 cubes. Start with first case. The first cube is red, and it is not replaced. Now we have only 1 red cube out of total 5 cubes. Probability of second red cube is selected. P equals 1/5. This is written as probability of event B after the event A is over. The P, B/A equals 1/5. So P, A mathematical intersection symbol B equals P, B/A times P, A equals 1/5 times 1/3 equals 1/15. Case number 2. The first red cube is replaced before second cube is selected. P, B/A equals 1/3. So P, A mathematical intersection symbol B equals 1/3 times 1/3 equals 1/9. Independent events. Event A and event B are said to be independent if the probability of event B occurring is not influenced by event A occurring. Mathematical definition: 2 events A and B are independent if and only if P, A, B equals P, A, it means the probability of event A after the event B is same as the probability of event A. P, B/A, the probability of B after A is same as the probability of B. A convenient definition: 2 events A and B are independent if and only if P, A intersection B equals P, A times P, B. This definition can be used as a test to decide if 2 events are independent. However, as a rule of thumb, if 2 events are physically independent, then they will also be statistically independent. There are a few points that should always be considered when dealing with independence. Number 1. Never assume that two events are independent unless you are absolutely certain that they are independent. Number 2. How can you tell if two events are independent? A good rule of thumb is, if they are physically independent, and they are mathematically independent. Number 3. Make sure that you understand the difference between mutually exclusive events and independent events. Mutually exclusive events mean that the events A and B have nothing in common and no intersection. A mathematical intersection symbol B equals phi, or probability of A intersection B equals 0. Independent events means that the outcome of event A will not influence the outcome of event B. P, A mathematical intersection symbol B equals P, A times P, B. Number 4. Independence need not be only for two events, but more than two also. So for three events A, B, C, probability P, A mathematical intersection symbol B mathematical intersection symbol C equals probability P, A times probability P, B times probability P, C. Number 5. Two events, A and B, are independent if the product of probability P, A times P, B equals probability P, A mathematical intersection symbol B. You may verify by determining it by other means. Number 6. Do not confuse the multiplication principle with the rule for independence. Multiplication principle is P, A intersection B equals P, A slash B times P, B. Independence is given by P, A intersection B equals P, A times P. Example number 11. Two fair dice are rolled. Find the probability that two even numbers will show up. Probability to show even number, P, even number, equals 3/6 equals 1/2. Let the A denotes the events, an even number, on the first die, and B denotes an even number on the second die. In this case, the events are physically independent, as the outcome on first die will not influence the outcome on the second die. Therefore, we have P, A and B equals P, A mathematical intersection symbol B equals P, A times P, B equals 1/2 times 1/2 equals 1/4. Example 12. Deborah has a chance of 0.7 of winning the 100 meters race and a 0.6 chance of winning the 200 meters race. A. Find the probability that she only wins one race. B. Find the probability that she wins both races. Let event A is Deborah wins the 100 meters race. P A equals 0.7. And B event is Deborah wins the 200 meters race. P B equals 0.6. If Deborah wins only one race, she must either win event A, the 100 meters, and lose the 200 meters, not B or B prime, or win event B, the 200 meters, and lose the 100 meters, not A or A prime. That is, P A intersection B prime equals P A times P B prime is equal to 0.7 times 0.4 equals 0.28. Also P B intersection A prime equals P B times P A prime equals 0.18. Therefore, the required probability that she only wins one race is P A mathematical intersection symbol B equals 0.28 plus 0.18 is equal to 0.46. B winning both races means that Deborah will win the 100 meters and 200 meters race. Therefore, we have P A mathematical intersection symbol B equals P A times P B is equal to 0.7 times 0.6 equals 0.42. Notice how we have made repeated use of the word and. This emphasizes the fact that we are talking about the intersection of events. Example number 13. The seeds are planted, each one having an 80% chance of germinating. Find the probability that A. all 4 seeds will germinate, B. at least one seed will germinate, A. let RE denote the event that the ith seed germinates. This means that P A1 equals P A2 equals P A3 equals P A4 equals 0.8. Therefore, P all 4 seeds germinate equals P A1 mathematical intersection symbol A2 mathematical intersection symbol A3 mathematical intersection symbol A4 equals P A1 times P A2 times P A3 times P A4 is equal to 0.8 times 0.8 times 0.8 times 0.8 equals 0.4096. Example 14, 13b. The seeds are planted, each one having an 80% chance of germinating. Find the probability that at least one seed will germinate. At least one seed will germinate includes 1 seed, 2 seeds, 3 seeds, and all 4 seeds will germinate and exclude only one outcome when no seeds will germinate. The probability that seed will not germinate is P A with macron equals 0.2. Therefore, P all 4 seeds will not germinate equals P A with macron 1 mathematical intersection symbol A with macron 2 mathematical intersection symbol A with macron 3 mathematical intersection symbol A with macron 4 equals P, A with macron 1, times P, A with macron 2, times P, A with macron 3, times P, A with macron 4, equals 0.2, to the power of 4 is equal to 0.0016. Now, P, at least one seed germinate, equals 1 minus P, no seeds germinate. Therefore P, at least one seed will germinate, equals 1 minus 0.2, to the power of 4 is equal to 0.9984. Multiplication law. We have 2 fair dice, one with numbers 1 to 6 on its faces, another with colors red, blue, green, orange, violet and yellow. If both dice are thrown together, what is probability of getting 6 in one and yellow on other? We make a table and note the event 6 and yellow. Outcomes of one die with numbers 1 to 6 is n, 6 equals 6, and favorable outcome is only 1, as number 6 on the uppermost. Probability of getting 6, P, 6, equals 1/6. Outcomes of another die with colors red, blue, green, orange, violet, and yellow is n, 6 colors equals 6, and favorable outcome is only 1, as yellow color on the uppermost. Probability of getting yellow, P, yellow, equals 1 or 6. Apply multiplication law of probability, which states that the probability of the joint occurrence of 2 or more independent events is the product of their individual probabilities, denoted as P, A mathematical intersection symbol B, is given by P, A mathematical intersection symbol B equals P, A times P, B. Therefore P, 6, yellow, equals P, 6, times P, yellow, is equal to 1/6 times 1/6 equals 1/36. Multiplication law of probability for dependent events states that if the outcome of one event affects the outcome of other events, such events are dependent events. Probability of the dependent events of 2 events is P, A mathematical intersection symbol B, is given by P, A mathematical intersection symbol B equals P, A times P of event B after getting event A, B/A. For example, 2 cards are selected without replacing the first card from the 52 playing cards. Find the probability of getting a king, followed by getting a queen. For first card P, K equals 4 of 52. For second card P, Q equals 4 of 51. P, a king and then a queen, equals P, K, times P, Q/K, equals 4 of 52 times 4 of 51 equals 16 divided by 26. 52 equals 1 divided by 166. For example, a cards is from a deck of 52 playing cards. Find the probability of getting a heart or a picture card, king, queen, and jack, or both. Let B be the event. A heart card is selected and K the event. A picture card of king, queen, and jack is selected. For a card of heart P, B heart equals 13 divided by 52. For picture P, K equals 12 divided by 52. Note, 3 picture cards are already included in heart. So for the event both, we have 13 plus 9 is equal to 22. Using the addition rule, P, B union set symbol K equals P, B, plus P, K, P, B mathematical intersection symbol K. We have P, B union set symbol K equals 13 divided by 52 plus 12 divided by 52 minus 3 divided by 52 equals 22 divided by 52. Bayes' rule. By Bayes' rule, we calculate the probability of an event A happening given the occurrence of another event B. The formula is P A slash B equals P B slash A times P A divided by P B, where P A slash B is the probability of event A occurring given that event B has occurred. P B slash A is the probability of event B occurring given that event A has occurred. P A is the probability of event A, and P B is the probability of event B. We take an example to explain. A box contains 3 blue balls and 7 red balls. A ball is drawn from the box, its color noted, and a ball of the other color is then added to the box. A second ball is then drawn. What is the probability that the second ball selected is blue ball? Let's RE denotes the event. A blue ball is observed on its selection, and by denotes the event a red ball is observed on its selection. For first event of draw, the probability of A, P equals 3, 10 and the probability of B, P equals 7 are 10. For second event, if first ball is red, then new ball added is blue. In this case, now box has 4 blue ball out of total 10. The probability of second blue ball, P, A2/B1, equals 4 or 10. Note again, if first ball is blue ball, then new ball added is red. In this second case, now box has 2 blue balls out of total 10. The probability of second blue ball, P, A2/A1, equals 2 or 10. Note it by setting up a tree diagram. In tree diagram, for event B of red ball, the branch is shown in red. The probability is 7/10. And for event of blue ball branch is shown in blue. The probability is 3/10. In second draw we have shown probability only for blue ball drawn. First case for second blue ball after red ball is drawn. Second line shows the case of second blue ball after the first blue ball drawn. Event A blue ball could have been observed on the second selection if #1. The first ball selected was red, A2/B1. The probability of second blue ball A2, P, A2 mathematical intersection symbol B1 equals 7/10 by 4/10. Number 2. The first ball selected was blue, A2/A1. The probability of second blue ball A2, P, A2 mathematical intersection symbol A1 is equal to 3/10 times 2/10. Therefore, P, A2 equals P, A2 mathematical intersection symbol B1 plus P, A2 mathematical intersection symbol A1 is equal to 7/10 times 4/10 plus 3/10 by 2/10 equals 28 divided by 100. Plus 6 divided by 100 equals 17 divided by 50. Bayes' theorem. Law of total probability. Watch carefully Venn diagram. Note event A, event B and not B or B' and B plus B' is universal set. So using the Venn diagram, for any event A, we have that A equals A mathematical intersection symbol epsilon equals A intersection B union set symbol B' equals A intersection B union set symbol A intersection B'. As these two events are mutually exclusive, we have P A equals P A intersection B plus P A intersection B'. However, P A/B tongue-poking smiley, A intersection B, divided by P, B, it implies P, A intersection B, equals PB times P, A/B. And so is P, A/B', which leads to the law of total probability. Therefore P, A, equals P, B, times P, A/B, plus P, B' times P, A/B'. Bayes' theorem for two events. As we saw earlier, conditional probability provides a mean by which we can adjust the probability of an event in light of new information. Bayes' theorem, developed by Reverend Thomas Bayes, 1702 to 1761, does the same thing, except this time it provides a means of adjusting a set of associated probabilities in the light of new information. For two events, we have the probability of event A after event B occurrence. The P A/B equals P A intersection B divided by P B equals P A times P B/A divided by P A times P B/A plus P A' times P B/A'. Example to explain Bayes' theorem for two events. A box contains 4 black cubes and 6 green cubes. A cube is drawn from the box, its color noted, and a cube of the other color is then added to the box. A second cube is then drawn. If both cubes are of same color, What is the probability that the both cubes selected were green? Note: first, both cubes drawn are of same color, and we want both cubes to be green. We begin by setting up a tree diagram whereby denotes the event a black cube is observed on its selection, and GI denotes the event a green cube is observed on its selection. A black cube could have been observed on the second selection if the first cube selected was green, i.e. B2/G1, or the first cube selected was black, i.e. B2/B1. Similarly, a green cube could have been observed on the second selection if the first cube selected was green, i.e. G2/G1, or the first cube selected was black, i.e. G2/B1. Note how tree diagram is made by yourself. From the tree diagram, that number 1 both cubes were black, and number 2 both cubes were green, and in both cases, both cubes were of same color. The probability of both cubes are green, given that both are of same color. The probability that they are of same color is given by the probability that they are both green or both black. P G2 mathematical intersection symbol G1 union set symbol B2 mathematical intersection symbol B1 equals 30. 100 plus 12 or 100 equals 42 divided by 100. Next, the probability P, both green given that both are same color, equals P G2 mathematical intersection symbol G1 G2 mathematical intersection symbol G1 union set symbol B2 mathematical intersection symbol B1 equals P G2 mathematical intersection symbol G1 mathematical intersection symbol G2 mathematical intersection symbol G1 union set symbol B2 mathematical intersection symbol B1 divided by P G2 mathematical intersection symbol G1 union set symbol B2 mathematical intersection symbol B1 equals P G2 mathematical intersection symbol G1 divided by P G2 mathematical intersection symbol G1 plus B2 mathematical intersection symbol B1 equals P G2/G1 times P G1 divided by P G2/G1 times P G1 plus P B2/B1 times P B1 is equal to 5/10 times 6/10 divided by 5/10 by 6/10 plus 3/10 by 4/10 equals 30, 100 divided by 30, 100, plus 12 or 100, equals 30 divided by 42, equals 5 divided by 7. Example to explain. Bayes' theorem for two events. In a small country town, it was found that 90% of the drivers would always wear their seatbelts. On 60% occasion, if driver is not wearing a seatbelt, they would be fined for speeding. Whereas, if they wearing a seatbelt, they would be fined for speeding 20% of the time. Find the probability that a driver who was fined for speeding was wearing a seatbelt. We begin by setting up a tree diagram where A denotes the event driver wears a seatbelt and B denotes the event driver speeds. We begin by setting up a tree diagram. Driver wears a seatbelt. Driver speeds. We identify when drivers were fined. Number 1. B/to B mathematical intersection symbol A. B2/to prime B mathematical intersection symbol A prime. We need to find the probability. P. Driver wears seatbelt given that driver booked for speeding, who was fined for speeding, was wearing a seatbelt. Equals P A/B. From the tree diagram, the probability P. Driver wears seatbelt given that the driver booked for speeding equals P A times P B/A is equal to 0.9 times 0.2. The probability P. Driver not wears seatbelt given that the driver booked for speeding equals P A prime times P B/to prime is equal to 0.1 times 0.6. Therefore, P. Driver wears seatbelt given that driver booked for speeding the P A/B equals P A intersection B divided by P B equals P A times P B/A divided by P A times P B/A plus P A prime times P B/to prime. Therefore P A/B is equal to 0.9 times 0.2 divided by 0.9 by 0.2 plus 0.1 times 0.6 equals 18 divided by 24 equals 75%. Thank you very much for watching this video on the topic of the probability. Please continue to watch our other videos by subscribing this channel's